Mm. Okay, so let's start. I am Abhinav Chandrakar. I am the TA for this NPTEL course, Strength of Materials, which is being taught by Professor K. Ramesh. I am the TA along with the other TA who is Archita Gogoi. She takes the courses on Saturdays. So today we'll be covering the doubt and problem solving session for week 8 of the course. This will be majorly concerned with bending and beams. So I'll be covering the first two lectures of the course, first two lectures of the week 8 lectures. So these are majorly concerned with firstly some introduction to bending, and then how you can mathematically represent the stresses and strains involved in bending. What are the assumptions? So all of those. In the third lecture, there are some engineering analysis techniques which Sir tells, along with some applications and examples of it. So that will be taken by Archita. So I let's wait for 2-3 more minutes, then we'll start. So as we do in every problem solving session, I'll first cover some of the key concepts which were taught by Sir in this week's lectures. And if there are any doubts, you all can ask, the participants can ask. And after that, we'll look at the assignment questions. Okay, let's start. Yeah. Previously, we had looked at torsion in the previous week's lecture. Uh, so in this one, so started with what are different kinds of loads that we can have. We can have along with torsion, transverse loading, and then we can also have axial loading. So the convention is that when transverse loading is being applied, we call it a beam, and that is a beam is experiencing loading. And if it's an axial load, that is along the axis of the member load is being applied, then we call it a bar. Just to separate out based on the loading for which the member has been made. And in case it is torsion, we call it a shaft. For example, ones which are used in some kinds of pumps or motors, right? So then sir explained that there are certain situations in which you can, for a particular loading, you can find out what are the forces and the movements which are being experienced at different paths, at different points in the members. But there are certain kinds of loadings in which you do not have that possible. It's not possible to find the exact forces and movements. And those cases are called statistically indeterminate loadings. So in such cases, if you consider the members to be rigid and non-deformable, then it's not possible to find out the forces being experienced. But if you consider them to be deformable, and that some small deformation is happening, in that case you can find out what is the force and movement which is being experienced. Also, uh, that explained that if you have a force which is acting on a body at a particular point, and you know want to know what is the uh, force and movement being experienced at a different point, then you can mm, move the force such that then you can move the force to the point of concern where we want to know what is the state, and also add a movement so that the kind of loading which is being applied will be identical to what was earlier. But now you can know what is the state of uh, what is the force and movement being experienced at that particular new point. So sir had told how you can do that, and that is helpful when you want to draw the shear force and bending moment diagram for any kind of loading. If you do this, it can be quicker to make this diagram. Also, sir mentioned about the convention which is which we'll be using when making the shear force and the bending moment diagram. So it will be as follows. If you have if you are seeing the left side of a member and the shear force is downwards, you will call it positive. So on the left side, if the shear force is downward, it's positive. But on the right side, if it is upwards, we'll call it positive. And if it is negative, if it is of the opposite sign, like the opposite direction, then we call it negative. Similarly, if there's a member which is experiencing some bending movement, and if we are looking at it from the left, and the bending movement is clockwise, we call it positive. If you are looking at it from right and it's anti-clockwise, then also it's positive. And if it's in the other direction, we call it that the bending moment is negative. So that is the convention we'll be using for making the diagrams. And when transverse loading is being applied, it's almost always necessary to make these kinds of diagrams. So it's good to understand these things well. Mm. Also, we have what sir started with was pure bending, which is the most simplest case of transverse loading, where there is only a bending movement being experienced, no net other forces there, no shear force is being experienced. Hmm. Also, sir pointed out that when you are considering a rigid body, then it is possible to get the forces that are acting at a point, the force system at a point. But when you have a deformed body, then there will be a distribution of the forces and movements, and it will have different values at different points due to different degrees of deformation. So there you will be looking more of a force distribution instead of force at a single point only. Mm. So when we are trying to study all of this and trying to form some relationships to mathematically look at how we can mathematically understand how the loading is happening and how what are the stresses being experienced. There are multiple assumptions that have to be made and which have to be kept in mind when you are making these assumptions. So earlier also it was said when we were studying torsion that we'll only be considering slender members, which means that the lengths of the members are much larger than the cross section area. Also here for now we are assuming pure bending to keep it simple and understand what kind of stress state is present in case of pure bending of a member. Also we are assuming symmetry is there. So the mm, plane of symmetry of the member uh, of the cross section of the member is same as the loading plane. So what how we can understand is the cross section of the member that which you are loading that has a plane of symmetry, and the loading will also occur about that plane on that plane of symmetry only, on that plane only which has this symmetry. Next we also have the assumption of isotropy. So just like we did for all our previous studies, almost all of what we looked at. So when we want to form mathematics, we always have to simplify, and isotropy is the first assumption or the most um basic assumption we made. The benefit of it is that once you consider something to be isotropic, then you can say that normal stresses will only cause normal strains, and shear stresses will only cause shear strains. So this demarcation can happen, and that makes the analysis of the stress state much more easier. Also, when trying to study the curvature of the member, let's say a beam, which is undergoing pure bending, we have represented the curvature as d phi by ds, and sir has told how what exactly is the angle phi. Phi is the angle which is made by the member when it is bent. So I'll have to show it in a diagram, and but this is fine. So and this is equal to 1 by rho, where rho is the radius of curvature. So you can understand that the more a member is bent, let me draw it. The more a member is bent, the smaller its radius of curvature will become, and the higher will be the value of rho. Um, Curvature would be, sorry. So the more member is curved, the radius of curvature will be of course smaller. So rho will be smaller, but curvature value will be higher. What I said was the opposite. So um, we'll also be using this later on because this gives you an idea of the degree of strain when you are bending, right? Because the more your member is curving, it means that it's undergoing more strains, and if it is undergoing more strains, then that will mean that the radii of curvature is reducing. So with that definition understood, we'll move to understanding or just seeing what are the expressions we get when we try to relate the stresses and strains occurring when you are looking at pure bending. Also, of course, we'll be looking at small deformation only. So, till now, almost for everything that we did, we also considered this assumption that we only look at small deformations, which makes the mathematics much more easier. You can just ignore many of the higher order terms that occur when you are solving. The solution for pure bending loading was first given by Euler-Bernoulli, and it's called Euler-Bernoulli hypothesis. The hypothesis, and this is important to understand. So the hypothesis is that if you have a member and it is bent as shown here by applying some movement, then the planes on the cross section, which were present in the initial undeformed sample, after being bent, the planes will still remain planar. They will not curve. So that is the hypothesis that Euler-Bernoulli gave, Euler and Bernoulli. And there will be one axis which goes from between, which was initially uh, linear in the undeformed member, but that axis uh, in the curved member will still have zero strains, so it will still be of the same length, and we call it the neutral axis. Also, since all the planes on the cross section are still linear, when you extrapolate them, they will meet at a single point, which means that this center member, which has been loaded in pure bending, is a part of a arc of a circle, with a radii which is equal to this value rho, radii of curvature. We can also understand that as you move along on the sample from the outer surface to the inner surface, mm, you can consider the outer surface as being negative y and the inner one as being positive. So as you move above above the neutral axis, positive y, the axial strain will be the strain that is being experienced will be compressive, because the material is being you can understand that the material is coming closer together and it is undergoing compression. Near the outer surface it will be tensile, and we can uh, look at what the axial strain will be experienced, what is the strain being experienced at any height y. So it is given by epsilon x equal to minus dou phi by dou s, the curvature value, into y, the height at which we are looking at the axial strain. Also, dou phi by dou s, the curvature will be constant for a particular amount of bending moment applied. So we can see that there is a linear variation of the axial strain along the y direction. Also, the shear stresses on the x plane in the z direction and on the x plane in the y direction are going to be 0. The axial stresses also in the y direction and the z direction are going to be 0. And then sir also showed that the shear stresses in the yz direction will also be 0. We can make that assumption. So actually, these are just some assumptions that we are making here. And sir has explained why we have been able to make it. These are because of the slender member assumption. Hmm. Okay, so from this we can understand that we have only axial strain, and that too only it's in x direction. Also, we know that the variation of that strain is going to be linear with y. So the state of the stress is not so complex. It's pretty simple inside this bent beam for pure bending. Also, normally we'll have a curvature occurring called anticlastic curvature, which will be something like this. So hump here, but here you will have a valley. So this is called anticlastic curvature. In uh, real members, it will be like this in practical scenario. But because we are assuming small deformation, we'll ignore it for our consideration. Hmm. Additionally, when we uh, want to relate uh, the axial stresses and strains with the bending moment which is being applied. For doing that, we can assume we can do force balance as well as movement balance. And when we do that and solve it, what we get is that the bending moment being applied is equal to E by rho into the moment into the second moment for that cross section. You can call it moment of inertia also, or the second moment for that cross section. So from this we can understand that MB equal to EIZ into 1 by rho, and 1 by rho gives you a measure of how much uh, strain is being applied, or how much strain is being experienced in the material, and MB gives you an idea of what is the bending moment that has been applied. So since EIZ relates the two, strain and the applied moment, it can also be considered as bending rigidity. It's known by this term also. Since if it is higher, it means that the member is more rigid, while if it's lower, it's less rigid, it's more flexible. Also, we can also write it like this. For torsion, we had something like this, which was somewhat similar, because there also the shear stress uh, linearly varied with distance from the center of your cross section. There we only considered circular cross section. So from the center of the circular cross section, the shear stress varied linearly from 0 to the maximum value. And there we had G phi by L. There phi gave you a measure of the torsion strain that was experienced, or strain present due to torsion. And here you can say that GIP is a measure of the torsional rigidity. Phi by L gives you an idea of the strain. So this way, if you relate it, then you won't have to remember too many things. It will be much more easier to retain all of this and understand this more intuitively, the mathematics of it. So one major benefit of this kind of understanding, which can be directly seen in applications, is the railroad, which sir showed. So instead of having a square cross section, which is more straightforward when making rails on which the wheels of the trains will move, we have this kind of a cross section, something like this. So a T kind of a cross section. Here also you have this thing as a base. And the reason we have it, now I think you all should be able to understand. The reason we have it is because the bending rigidity is more dependent on I value, the moment of inertia, and when we are making this kind of a railroad, we want it to be more rigid, because if it will undergo too much of strain or deformation, then it can plastically deform and the life of that railroad will reduce. We want it to experience as little of uh, strain as possible. The bending moment, of course, will be fixed, because it will depend on the load applied, the contact of the wheels with the railroad. So that will depend on the load being applied. But you can change the either the material being used or the geometry of that railroad which is undergoing loading. If you want to look at the geometry, then you what we'll try is to have a high value for the moment of inertia so that we have a high bending rigidity, while at the same time having to use lesser amount of material to reduce cost. So if you use a kind of a square cross section, then the amount of material you will have to use will be high. While if we use this kind of I kind of cross section, then the amount of material will be lower because you are removing not using material at this point these points. So from here you have removed some material, but still being able to retain most of the bending rigidity because the moment of inertia is higher since you have material at farther distances. So it will be moment of inertia will have greater contribution for material which is farther than from one which is closer to the center. So that was the idea why we have these kinds of railroads. Now let's move on. Also earlier we have seen that the condition for equilibrium based on elasticity theory is dou sigma by dou x plus dou tau yx by dou y plus dou tau zx by dou x plus x, the body forces, is equal to 0. This is the relation for equilibrium. I think here there's some mistake. I'll correct it. Here it should be tau tau zx by dou z. We are looking at the equilibrium in the x direction, but we are also looking at the contribution of shear stresses on the y plane and the z plane. Also, for those who might be having some doubt, here I'll explain the railroad situation. So, if this is the member being loaded, this might be the railroad, and this is the cross section plane on which loading is occurring, right? So, this is the kind of loading. So, we want IZ to be low for this particular about this plane. The about this plane, we want the moment of inertia to be low. So, since the material which is closer to this plane will mm, hmm. Actually, the loading is not occurring like that. That was why I was confused. Hmm. You have normal stress is being applied here uh, due to the wheels. So you have normal stresses and the reaction to it. But the wheels will also apply some bending moment in this direction. Let's just think about it more clearly. Mm. Mm. Okay, I'll look at it again later. That's the railroad problem. I'm a bit confused about how the loading is. But let's continue with the summarization. Mm. Also, when we are considering more complicated loading, because almost never have pure bending, since whenever you apply any kind of load, there will be some forces, some shear forces will be there. When you have a transverse loading, so this kind of pure bending will not be occurring, but we can still use the results of pure bending for these more complicated bending, uh, 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 complicated situations. And there are certain assumptions we make and certain conditions which allow us to make these assumptions without being too wrong. So the important thing is to not be too off and what uh, know how much error you might be making when making those assumptions. So what we call it is called engineering analysis. And here we make this important assumption that the shear force effects will can be treated as being separate from the bending moment effects for slender members. And sir has shown that if you do that, if you consider shear force effects as being separate, then for a loaded beam, we'll we'll have this kind of a expression, the relationship between the bending moment and the shear force. So the slope of the bending moment diagram will be negative of the shear force diagram, the value of shear force at any point. So this allows us to relate the shear force diagram and bending moment diagram for any kind of loading, and that makes it easier to make these diagrams. Also, we have this assumption that the so here we had pure bending, right? So there was a particular bending moment that had been applied. But if you have a kind of load where the beam is experiencing different values of bending moments at different points, then it might be possible that the mm Euler-Bernoulli hypothesis might not hold. That is, the axial strain distribution with y might not be linear. But here we'll assume that it will still be linear and that the value of the axial strain distribution or the linearity will depend only on the magnitude at the point where we are looking, the magnitude of the bending moment. So we'll only look at the bending moment value at that particular point, and using that we'll calculate the axial strains, assuming that the results of pure bending still hold. Also, when shear stresses are being applied, of course, there will be the planes which were present in the undeformed beam. So those planes in the cross section, they will no longer be planes after shear force stress is applied. But here we'll again assume that for slender members, the shear stresses will be concentrated only near the middle. And because of that, we can still consider the planes to still be planar after the load is applied. All the shear stress is acting at the middle only. And of course, at the surface, it is zero, since stress vector at surface is zero. Mhm. So that was all which was covered in week 8 in the first two lectures. Now we can move on to the assignment. So it was decided, okay, I forgot to inform that it had been decided earlier that from now on we'll not be covering the assignment questions of this year, that we will not solve them. Since the NPTEL staff and the professor prefers that you all try to solve it by yourself, by based on the understanding you gain from the lectures. And once you have solved it and submitted it and it has been assessed, after that, once the solutions get released, if you have any issues or any doubts, you can bring that up in the subsequent problem solving sessions, and then there we'll address it. So we won't address the assignment questions before the submission deadline. After that only we'll look at the doubts. So instead of covering the assignment questions, we'll cover some other questions which are not part of the assignment, but still related to these concepts only. Also, since we do not have much of a crowd today, and we have some time, we can look at that railroad thing where I was confused, the kind of loading we have there, and why the cross section which we are using there is optimal from a bending point of view. So let's go there. Mm, 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 mm. Yeah. Okay, so I hope this will looking at this it a bit more clearer where I was getting stuck when explaining the railroad, the loading in railroad and the bending movement that will be experienced. So let's say the railroad is like this, and actually the wheels are somewhat like this. So you have one wheel here outside, and that wheel is like this. It's something like this. Yeah. So there's a axial force being applied. Sorry, there's a contact force that is experienced here, and this will be a normal force. So there will be a normal reaction to it also, but also this will try to bend it like this, so in this fashion, right? And we need to resist that bending. Mhm. I'm still a bit confused. I'll look at it more and maybe tell in the later class if anyone has a doubt on this. But let's now move to the assignment. Okay, let's go through the questions. The first question is, when a rod or a cylinder member is subjected only to a transverse loading, it acts as a, we know that if it's axial, we call it a bar. If it's transverse, we call it a beam. And if it's torsional, we call it a shaft. So the correct answer will be uh, sh- shaft. A beam is said to be under pure bending if it transmits. You have already looked at this. If the value of bending moment is constant all over the beam, only then we call it pure bending and we should not have any shear stresses involved or shear force involved. So the correct answer is only constant bending moment along its length, no shear and no change in the value of the bending moment. Third question is, for a beam having square cross section made of a single material subjected to pure bending, the neutral axis will coincide with the, hmm, line of action of the applied load, centroidal axis of beam's cross section, maximum stress point of the beam, and topmost portion of the beam's cross section. So the neutral axis is the one which passes through the beam, and it is the centroidal axis of the beam's cross section. So you can understand it by looking at the derivation of uh, how we get epsilon x equal to minus of dou phi by dou s into y. So the y we consider here is starting from the neutral axis, which is the axis where you do not have any axial strain, and that will always be the centroid of that cross section along the y direction. Next question. Line of action of the applied load. Let's also look at the other option. Line of action of the applied load will depend. I'm not sure about what line of action will mean. I think where the load is being applied, that line. Maximum stress point of the beam. This can be either the top or the bottom of the beam, depending on, of course, whether the cross section is symmetric, the symmetry of the cross section is. For a square cross section, it can either be the top or the bottom. For both, it's same, just the sign is different, tensile and compressive. Yeah, topmost portion of the beam's cross sections. Also, this will not be the neutral axis. It will have some strain. Next question. The plane perpendicular to the plane of symmetry through which neutral axis passes through is called. Hmm. So that plane is called the neutral plane because on that whole plane, if you are assuming pure bending and slender member, so all those assumptions are being made. Isotropy, all of those assumptions. Then in that case, the whole of that plane through which the neutral axis passes, and it is perpendicular to the plane of symmetry. So to make it more clearer, if you have this kind of a beam, it is undergoing bending in this way. So this is the plane of symmetry through which the neutral axis is passing. This is the neutral axis, right? Going through, I think this point, maybe you can say. So this is the neutral axis passing through the centroid where you will not have any axial strain. It is like this. It passes through this plane, this plane of symmetry, and the perpendicular plane where we are saying there is not going to be any deformation is going to be this plane. Let me write it like this. So the plane like this, and this we call the neutral plane. So for to make it more clearer, mathematically we can say that here the y is going to be 0 because it lies on the centroid. The y position is the centroidal position. Centroid's y position. Yeah. Next, let's go to the next question. So we have a beam undergoing pure bending. The curvature is like this. What will we call this kind of curvature? So we call it anticlastic. The reason for that is that if you look at this point on this plane, let me see, on this, if this is mm, x, y, and z plane, then if you look at the yz plane and look at this curvature, then it is positive. While if you look at the at this curvature on the xz place, then it is upwards. So this was downwards. Let's not call it positive or negative. This was downwards. This was upwards. And because they are in opposite directions, that is one reason why we call it anticlastic. And that is how the material actually deforms when it is bent. But we just assume it to be having the same cross section even on bending for simplicity. Now let's go to question 6. We have a canopy and we have to identify what kind of beam is being used in this construction. So let's look at where the beams are. These are the beams which are taking the load of the roof, the glass roof which can be seen. These are beams. And here we can see that it is experiencing a load, a distributed load at all points due to the weight of the roof. So we can see that it will undergo majorly bending. There's a bending moment which is being applied with respect to this point, which is hinged to the wall. So it's a transverse loading, and we call it a cantilever beam due to this reason. The next, this is the last question. Identify the correct statement. Let's look one by one. First question is beam theory is applicable for a cross section that has a vertical plane of symmetry and the loading is in the same plane of symmetry. So this is true. This was the kind of loading we used and the cross section we used when we looked at beam theory. That was pure bending. The next option is the material of the beam is considered to be isotropic. So we also made that assumption. Based on this, we were able to say that all the other axial strains except from that in the x direction, all the other normal strains and the shear strains will be zero. Sorry, the normal stresses and shear stresses will be zero, not the strains. since Poisson's ratio will also be applicable there. Mhm. A plane cross section of the beam remains plane during the bending. Yes, that is true for pure bending according to beam theory. Shear stress distribution in the beam is uniform across the cross section. That will be false since in beam theory we are considering only pure bending, no shear stresses. Then internal stresses are proportional to the distance from the neutral axis. Mm. This is also true. We have seen that epsilon x is linearly proportional to the value of y, and the proportionality is minus of dou phi, the curvature, by dou s. So we have linear proportionality. This is also true. Yeah. With that, the questions are over. For those who want to look at this, they can find this PDF in my shared drive folder. So you can go there and again look at these questions. Also, these are questions from previous year's assignment for this course. With this, we are, I think, done for today's doubt solving session. Since nobody joined today due to some reason, also since it's a holiday today, I didn't realize that. So because of that, we quickly finished it, but I'll just wait for 15 more minutes in case someone joins us has some doubts. So we'll just wait 15 minutes. Otherwise, we'll meet again next week for the next week's lecture content.